Hey guys, last time we discussed Riemann sums. Now in section 5.3 we would like to define definite integral using Riemann sum and see its properties. Learning objectives are: first we will define definite integral using Riemann sum, then we will give the properties of definite integrals, then we will see the relation between area and definite integrals, and finally, we will do some examples on how to find average value of a continuous function. So let's get started. So let's start with the definition of definite integral. So again, if you remember, we considered Riemann sum, right? What was the Riemann sum? Well, we first pick a partition from an interval AB, right? And then from each partition, we pick one representative, one number, which we call CIs. And then the Riemann sum was f of Ci times delta x, right? And the sum runs from 1 to n. So now, how do we define the definite integral using Riemann sum? So I'm not going to give the full definition of integrability or integrable function, etc. I would like to only concentrate for continuous functions because that's what we will be doing mostly. Okay, so what is the definition of the definite integral for continuous functions? Well, given the continuous function f of x on an interval AB, as before, I divide, so I consider partition, right? So I subdivide the interval AB into equal width subintervals, right? So each length of the subinterval is b minus a over n, right? And then I choose one point xi star from each subinterval, okay? So then the definite integral is simply defined as limit n goes to infinite of this Riemann sum, okay? And as you can see from the definition is independent of your choice xi star. So if you pick xi star, let's say from the left endpoint of the subinterval, if your friend chooses from right endpoint, if someone else chooses from the midpoint, it doesn't matter. At the end of the day, you should get the same limit. And this is for continuous functions. Okay, so this symbol is called the integration symbol, right? So the lower limit a and the b is the upper limit. This is this s looking. You remember Riemann sum was the signal notation coming from Greek alphabet. It also stands for s, right? So it's the sum. So similarly, integral is also like s looking symbol. So you can sort of remember that the integral is some version of summation. And then we have f of x, which is called the integrand, and then we have this dx. Okay, so where x is the variable that I'm looking for. All right. So here is more explicit formula. In the previous slide, we had f of xi star here. Now we pick this f of xi to be the right endpoint of each subinterval. So again, let's recall. So my a was x0, right? Then I had x1, then I had x2, etc. At the end, I had xn, which was my b, right? And I have these sub-intervals, right? Okay, and xi star, or in the previous section we called ci. Anyway, so it's some point that's picked. So like x1 star is picks some point picks from a to x1. But now let's pick this xi star to be the right endpoint. Yeah. So then what is my x1 star, for example, right? What is my x1 star? So what is the right endpoint of the first interval? It's x1, right? But what is x1 again? This is for equal widths, so each interval is of equal length, which means delta xi is nothing but b minus a over n. So I start from A, and if I move to x1, so x1 is b minus a over n distance apart, so which means this x1 can be found from x0, right? So x0 is a plus b minus a over n. Indeed, if you let this k equal to 1 here, right, this is what you get, right, etc. So basically the general formula for xi is a plus I times b minus a over n. So here the variable is k, right? So k runs from 1 to n. So in place of a, I, if you like, you can consider k. Okay, and for the Riemann sum again, so it was f of xi star multiplied by delta xi, but because we fixed delta xi, it's ba over n, right? So that's what's justified here. Okay, so this is when you pick your xi star to be the right endpoint. But as I said, I mean, you could pick left endpoint, then you would get slightly different formula. So here you would sort of start from k0 to n minus 1. You could pick the midpoint, etc. So there are different versions of the same definite integral. But for our purposes, we can pick this particular definition when we do example. The properties of definite integrals are as follows. If you integrate from b to a of a function, it's the same as integrating from a to b, but with minus. So the sign is going to change if you swap the limits of the integration. Then there is zero-width interval. So if you're integrating from a to a, right, so essentially there is no interval, then in a sense your delta x is going to be 0, right? So it means the summation will be 0. The constant multiple, so you can always take out the constant, right? So you can factor it out. This is also easy to see. So basically, all these properties can be derived from this Riemann sum. So if you write all these things as a limit of Riemann sum, then you see what's happening. The fourth one is the sum of the integral, the integral of the sum is sum of the integrals, or integral of the difference is difference of the integrals. Additivity, what is additivity? So if you integrate from a to b and then from b to c, it's the same as integrating from a to c, right? A special case could be the following. You're integrating from a to b and then from b to c, right? So integrating from a to b, b to c, it's the same as integrating from a to c directly. Max mean inequality says the following. Let's say that I have a maximum of f and a minimum of f. In fact, on AB, if I assume my function f is continuous, right, we know by extreme value theorem that minimum and maximum exists. Then here's the relation. The definite integral always falls between minimum f times b minus a, maximum f times b minus a. Again, this is sort of easy to see from the Riemann sum. If you remember, the Riemann sum definition was f of xi delta x, right? So if I replace this f with minimum, it will be less, right? I will make it smaller. If I replace by maximum, I will make this bigger. So that's why this, if you like, by the sandwich theorem, the integral falls between the min and the max. Okay, domination. If one function is greater than or equal to another function, then the same inequality is respected when you integrate. So when you integrate, the inequality is not going to change. So a particular case is when you let g equal to 0, meaning if your function is non-negative, right, if it's positive or non-negative, then integral will also be non-negative. Okay. As I said, I mean, all these properties follow from the Riemann sum. I would definitely suggest for the students to try it out, to try to prove it, and then, if necessary, ask me or your practice instructor during office hours. Let us illustrate the properties that we saw with examples. So let's say that I know these three quantities, that integral from -1 to 1 is of f is 5, integral from 1 to 4 of f is -2, from -1 to 1 of h of x, the different function is 7. Now let's say that I want to find the integral from 4 to 1 of f of x. What happens? Well, I know the 1 to 4, right? So we know that if you swap the integral, so the limits of the integral, then the sign will change. So this is minus of 1 to 4 of f of x dx. And now I know that the integral of f of x from 1 to 4 is -2. So this is negative times the -2. So this is 2. In the next, we can use uh, the summation rule, right? So we can say, yeah, let's not hurry. So I can write like 2 f of x dx plus the integral from -1 to 1, 3 h of x dx. And in the next, I can factor out the constants, right? I can write this as 2 times the integral from -1 to 1 f of x dx, and then plus 3 times the integral of h of x from -1 to 1 of with respect to dx. All right, so integral from -1 to 1 of f of x is 5, so this is 2 times the 5, plus 3 times the h of x, the integral of h from -1 to 1 is 7, that's what we get. So 10 plus 21, 31. Okay, now, what next? I want to integrate from -1 to 4 f of x dx. So for f of x, I have the two integrations, right? 5 and -2. What do I do? Well, I can write it as follows, right? So integral from -1 to 1 f of x dx plus the integral from 1 to 4 f of x dx. Now the first integral is 5. The second integral is -2, so it makes 3. Okay, another example. So we want to show that integral of 1 plus cosine x in square root from 0 to 1 is less than or equal to square root of 2. Well, we have the max-min inequality. Let's recall it. So integral from 0 to 1, square root of 1 plus cos x dx is less than or equal to b minus a, which is 1 minus 0 times maximum of square root of 1 plus cos x, right? Maximum of the integrand. But where are we taking maximum? We are taking maximum from 0 to 1. What is the maximum value that this square root of 1 plus cos x can get? Well, we know that cosine x is always less than or equal to 1. In fact, when 0, right? At 0, cos 0 is 1. So this maximum value, we see that it's square root of 2, right? So this whole thing is simply square root of 2. Area under the graph of a non-negative function. So here's the definition. If my f of x is non-negative, which means f of x is greater than or equal to 0, or over the closed interval ab, then the area under the curve of y equal to f of x over ab is nothing but the definite integral from ab of f of x dx, right? So this is a definition, but why this definition really makes sense? Why does it make sense? And what does it mean under the curve? Well, I need to sketch, here's my a, here's my b, I need to sketch an f of x about the x-axis, right? Because it's bigger than or equal to 0. So it might be some function like this. So that's my y of x. And area under the curve means the area bounded between this curve and x-axis, okay? So that's the area that I mean. But why it really gives us this definite integral? Well, if you remember the definition of the definite integral, what we did was we split definitely to calculate this definite integral, we split the interval AB into let's say n pieces. So here I'm sort of divided into 4 pieces, right? And then, if you remember, we pick, for example, right endpoints, right, for each interval, and then we calculated the Riemann sum. So what was the Riemann sum? Riemann sum was f of this xi star times delta xi. So if you remember again the section about the Riemann sum, what is f of xi? Now, because the functions are non-negative, f here is going to give me this height, right? Height of this particular rectangle. And this delta xi is just the width. So what I'm doing in here is I'm calculating the area of, let's say, ith rectangle, right? Ith rectangle, right? So this is first rectangle, second, etc. So for the second one, what's here? So here's my right hand point, and here is the rectangle. So I'm calculating this area of this rectangle, and then I'm calculating the area of here, and if this is my point, I'm calculating this area right here. Okay, but this is so if I sum them up, definitely I'm not getting the area of the curve, right? Because here I see some extra points here, but here I see some missing points, right? Some missing regions. Here again I have some x-ray, etc. However, what was the integral? Integral is I split the AB into n pieces, right? Into n pieces, and I let n go to infinite. So I have lots of rectangles, right? So if I take the width to be go to 0, right? When I take delta x very close to 0, then my approximation will become more accurate, and in the limit I will get the area. Okay, so that's kind of the justification of this definition. And this is in fact an important observation that and important application of integral. That integral can be used to calculate area when the function is non-negative. Okay, so let's say that I want to compute the area of a region A under the curve y equal to x in this interval 0b. So if I want to sketch y equal to x is here, right? And I need to sketch it from 0 to b, so b is some point here. So I'm trying to calculate the area of this right triangle. Well, because y is equal to x, my height here, height of the triangle is also b, right? So what is the area here? If you simply use the geometry, right? The height is equal to b, the width of the triangle equal to b, so the area is b times b divided by 2, right? It's b squared over 2. Now let's see, let's apply this the definition in the previous slide and see whether we will get the same quantity. And in fact, this example is important because I will show you how you would compute the definite integral using a Riemann sum without using any integration rules, right? You might know that this integral is integral of x is x squared over 2, and you plug in b and the 0, and then you subtract. Yes, we will come to that point, but for now, I want you to learn how you should do it without using the properties, but merely using the Riemann sum definition. Okay, if you go back to the slides where we defined the definite integral for continuous function, and this y is equal to x is a continuous function, it was something like limit as n goes to infinite of the Riemann sum. Let's say k. Okay, let's use k from 1 to n. Here we use the right endpoint, so f of a plus k times b minus a over n times delta x. Okay, right? Now, great. Limit as n goes to infinite. K from 1 to n. What is my a? My a is 0. Right? And my f is here. My f is simply x. Right? So this f of k times v minus a over n simply becomes k times b minus a over n. Oh, by the way, a is 0, so this is simply b minus 0 times delta xk. I'm picking the equal width partitioning, which means in this case each partition will be b minus a, which is b minus 0 divided by n. Now, my here the index is k, right? So k is something that varies, which means b and n, they are constant. So I can take them out. N goes to infinite. So I can write here. I see b squared, right? So I get b squared over n squared, and then I need to sum k from 1 to n of k. Now, if you remember how we calculated this in the previous lecture, so this is the sum from 1 to n, right? So from 1 to n is the formula was n plus 1 divided by 2. Great. Now I got rid of this Riemann sum, right? There is no Riemann sum anymore. It's just this quantity, and now I want to take the limit as n goes to infinite. Well, now my n becomes my variable, so which means b squared is independent of n, so I can take it out, right? So I can take it out b squared. I can also take it out 2, and what is left here is I have n times n plus. Okay, so in fact I can cancel this n with one of the n's at the bottom. So then I will get n plus 1 over n. Now, what is the limit of n plus 1 over n? Well, we have two different methods. For example, you can apply the L'Hopital, show that it's this limit is equal to 1, so this becomes b squared over 2, right? This is indeed what we got using simply geometry. So that sort of justifies the definition that we provided for the area under the curve using definite integrals. Average value of a continuous function. Here's a definition. If f is integrable, so in our case, if you pick a continuous function, it is integrable, then the average value of the function over the interval a, b is given by 1 over b minus a times this definite integral. Why does it make sense, right? Again, we want to make sense of it. Well, again, if you remember what does it mean to take the average of a function, right? Or average of some quantity? Well, it would be something like f of x1. If you have n points, right? F of x1 through f of xn, and then you would sort of divide by n, right? So that would give you sort of the average if you had some discrete function or sequence, let's say. But we have a continuous function, so what happens is instead of this whole thing, what we have is the limit n goes to infinite. So this is the Riemann sum, k from 1 to n, f of x, I don't know, let's call it xi star times delta x. What was delta x? It's b minus a over n, right? So that part would be my definite integral part. But I also have 1 over b minus a, right? So I also need to write that that here. So here there's 1 over b minus a. Now you can see that this 1 over b minus a and b minus a will cancel. So what I see here is sort of limit of this sum, right? So this is like f of x1 star, etc., f of xn star, and then I divide by n, right? So it's very natural that this quantity gives us the average of a function, and in fact it has lots of applications, right? In real life situations. So this is an interesting another application of an integral. All right, so let's calculate the average value of the function given here on -2 to 2. By the definition, this average value is going to be 1 over b minus a, so this is 2 minus 2 integral from -2 to 2 of this function 4 minus x squared in square root dx, right? Okay, so how do we integrate square root of 4 minus x squared? One approach would be try Riemann sum, but this is very not easy because you have the square root, you have to handle lots of things. I don't know if it's impossible. Another option would be if you know how to really integrate, I don't know, maybe from high school, etc., then maybe, yes, you could do. However, we haven't seen the properties, right? So what we can do is we can use the area interpretation. The square root of 4 minus x squared, that's a non-negative function, right? So for non-negative functions, the definite integral is nothing but the area. So if I manage to calculate the area under the curve y equal to 4 minus x squared, right, on -2 to 2, if I somehow manage, then this definite integral would be equal to this area, right? Well, so let's try to sketch this curve. What is this curve? Well, if you square both sides, this is y squared is equal to 4 minus x squared, so you get y squared plus x squared equal to 4. So we see that this thing is the circle, but I don't have y equal to plus minus, so this is the half of the circle, right? It's a semicircle. So we'll get here's -2, here's 2. I'll get this. So this is my y equal to square root of 4 minus x squared, right? Because at x equal to plus minus 2, I intersect my x-axis. So it's a semicircle. The origin is at 0. And the radius, as you can see, is 2, right? So what is the area? So that's the area, right? This integral, the definite integral, is equal to the area. Well, what is the area? Because it's a semicircle, so we see, so this is 1 over 4. And here area of the semicircle is pi r squared, so pi r is 2 squared divided by 2, so this is pi over 2. That's the average value of the function.